Good afternoon. Welcome to JFuture, to my session about fast data. A little bit about myself. My name is Bas Geerdink. I live in the Netherlands, in Utrecht. And I have a background in artificial intelligence, but back in the old days. So my current data science skills are not as they should be, but still enjoying the field of AI very much. And I work mostly with big data, architecture, etc., technology leadership. You can find me on Twitter, LinkedIn, etc. Happy to connect. So we're going to talk about fast data or streaming analytics, which is a very popular subject nowadays. And to understand why, we have to go back a bit to the old days, to where the definition of big data was coined about 10 years ago by Gartner. They introduced the 3V model: volume, velocity, and variety. And a lot of talk has been about the volume of data, right? When we talk about big data, data is usually about analyzing historical big data sets to do machine learning on. But the velocity of data is also nearly as important, because velocity just means that data that comes in at high speed. And until maybe recently, it was very difficult to analyze this kind of data, because there were not proper tools for that. It was all very difficult to do so, and also the data sources were not that well equipped to produce this amount of data. But in the current enterprises, we can see a lot of use cases where this is becoming much more interesting, and also the technology is helping us to analyze this kind of data. So basically what we're talking about is any event stream that needs to be processed in real time. For example, in finance, you can call it, you can think about fraud detection, or in retail, trend analysis to make real-time recommendations to customers. And also think about when we want to analyze machine data, log data in the Internet of Things. So there's a typical pattern involved, and a typical, we could call it a reference architecture when it comes to dealing with this kind of data. The pattern that I want to talk about is these three steps. First, we want to do the pattern detection. Then we want to determine a action, a next best action, or a follow-up notification. And then we actually want to produce that notification. Why do we first detect patterns in historical, or in streaming data? Well, the reason actually is that usually one of the events that comes into our system that we want to analyze does not contain so much interesting information. It's only one event. It's only like one mouse click or one money transaction. It only becomes interesting if first you detect a pattern in the stream, and then once you have detected this pattern, step 2 is then to use that data and to enrich it with the historical data, for example, the other customer data that to make a prediction, to make a suggestion, for example. In architecture, this looks a bit like this. If we're going to analyze streaming data, we'll usually do it with an event bus. So the gray bar in the middle you see here is your event data stored in an event bus, such as Kafka. And your technology actually consists of streaming jobs that read and write to this event bus. And these three steps can actually be captured in 3 separate jobs. So we would have a complex event processing engine, which does the pattern detection. We would have a machine learning engine that enriches the data with your historical cache of your customers, and basically scores a model. And the outcome of that model, this score, this recommendation, can then be used to actually trigger a follow-up action. What's really interesting here is, of course, that we work with machine learning. I will dive a bit into that also as well in the next slides, because it has some specific requirements when you talk with streaming data. But as with any machine learning algorithm, the feedback that you can gather from your actions is very important. So if it's possible, you would have to not only produce a notification, but also produce a actionable notification, an actionable event. so that you can gather feedback from your customers to feedback into your machine learning model as your training data. What kind of technology can we use for this? Well, in the open source world, there's nowadays quite some tools that are quite interesting. The examples that I have today are with Apache Flink, which is one of the best streaming engines. I already mentioned Kafka as the well, basically the de facto message bus in this sense. Currently, for stream processing, also Spark Structured Streaming is a library on top of Apache Spark, is doing great stuff, and is also really a sensible choice for you to pick. And also, if you're working in the cloud, there's plenty of tools available nowadays that can help you analyze your stream. So we're going to do a bit of a deep dive and look a bit into the typical, problems and solutions and challenges that you might encounter when you're dealing with this amount of streaming data. Well, first of all, we have to think a bit about how we're going to do it. I already explained that we're going to do we're going to build streaming jobs that process data from an event bus, which is usually Kafka. So your application, as you would call it, is just basically a job that reads from Kafka and writes again to Kafka and does data processing in between. So what you do is you build a job that you deploy to a cluster, to a big data cluster. As I said, again, my examples are with Flink, but Spark works actually the same way. So what you do is you connect your engine to your data stream. You start consuming events. Then you usually should have a way to aggregate these events, and then if you're happy with basically the result of that aggregation in a window, then it's time to write again to your to another topic of your stream of your event bus. In Flink, it's actually quite easy to set up because Flink comes out of the box with, for example, Kafka integration. A Flink job in itself is just a Scala or a Java application. By the way, my talk has Scala coding examples because they were shorter and I think easier to understand. But Flink itself is written in Java, so you can pick whatever programming language you use, and you just start by adding these dependencies. Current version of Flink is 1.11 to your Maven POM file. After that, you have to write some code to connect to your stream. And as I said, Kafka integration comes out of the box already. So what we have here, we already expect that we have a streaming execution environment. Nice thing about these kind of frameworks nowadays is also that you don't need a big data cluster. You can also just set it up on your local machine and have maybe 1 or 2 worker nodes instead of a full-blown big data cluster. So you're perfectly fine with just programming Flink jobs on your local machine. What you do is you specify the schema that you want to read from Kafka, and you create this thing called the Flink-Kafka consumer. With you see here the read topic definition, so that's basically the topics that you want to read from, the schema that I just mentioned, and some other properties for connecting to Kafka. This gives you the raw event source, so the raw events, basically the base events that are coming straight from Kafka, and then you can just program against that by, for example, adding filters, maps, and thereby modifying your stream a little bit. And this already looks a bit like functional programming, or looks a bit like the normal functions you would write on, for example, a list or another collection of events. But of course, it's different. It's not a list, it's a never-ending stream of data. But we come to that later. Your job itself needs to be parallelized because yeah, else you would not have to run it in a big data cluster. So we really are focusing on use cases here that are, for example, where events come in with speeds of like thousands of events per second, for example. So if you want to process that in one machine on one node, it's too much. So there has to be a way to parallelize your data stream. Nice thing about Flink and also other libraries is that you can configure your parallelization on multiple levels. I picked these two to give you an example. First of all, your cluster itself needs to be parallelized, so you need and so your data needs to be distributed across certain number of nodes. For example, the number of task slots and task managers in a Flink cluster. But if, let's say, you have a cluster of 10 or 100 nodes, doesn't mean that every job needs to utilize all these kind of resources. Every job that you deploy to your cluster also can have its own parallelization configuration. And that means that you can actually really nicely configure your cluster. You have your ever running big data cluster there, but you might have like 10 jobs deployed to that all consume a certain number of resources, and that allows you to tweak your cluster in a nice way. But that's of course where it starts. So you know that, okay, I have a job running with a parallelization of 10. But now, how do I distribute my data across my system? You also need to write a function for that, and it's the key by function. And that's, of course, you need to think about this to pick a value in your event data that is sort of distributed randomly, or at least in a nicely distributed way. So that you don't force all your data into one node, while the other 9 are basically not doing anything. So this example, I created just created data stream, and I connected it to, I keyed by the customer ID.head, so the first character of the customer ID, and I can assume that's fairly random, because the customer ID is just a random number, basically. Now, once we are actually reading the stream, we have to think about the timing of things. And now things get interesting, and this is the typical things that you usually don't concern yourself with when you're not processing streaming data. But you have to realize that if we want to analyze data in the stream, timing is of the utmost importance. And actually, what we are really interested is something called the event time. And the event time is the timestamp of when the event actually happened. Now, why is that more interesting than the processing time, which is the time that we actually process or handle the event in our stream? Well, that's because out of orderness can occur. You see a stream of events here that occur just nicely after each other in event time, but the effect that a cashier can happen, it can happen that we have to wait just a little bit longer for a certain event to arrive, and that actually another one already caught up. So because the network latency, that's in between here, there's always some latency, of course, is unpredictable. So if the order of the events really matters, and usually it does, then you want to look at the event time of your events. And modern frameworks like Flink can actually take that into account. So when you're talking about the time of an event, they're not talking about the server time, the processing time, the wall time, etc. They're talking about the event time, which is actually the timestamp of the event, of the field of the event when it actually occurred. If you want to remember this, then think about Star Wars, because these movies of Star Wars actually also were in a very different order than in the universe that they actually occurred in. So the event time of the Star Wars movies is actually different from the processing time of the movies that we view them here on Earth. So Another thing that I already mentioned a bit is that we need some way to to aggregate data and to also to make it a bit more compact, because if you want to do machine learning on event data, on streaming event data, first of all, you don't want to do it on every event because that doesn't really make any sense. But you also want to take into account a certain pattern or a certain history of data, because that's when things get interesting. To give you an example, when I'm analyzing money transactions, I'm usually interested in, okay, how was the money being spent in the last day, for example, for a certain customer. If there's certainly a peak in that, or if that's on average it is very volatile, then might be a fraud case. Or if, for example, I detect a certain pattern that the amount of money that somebody is spending is going down drastically, then I might give him an alert. So I'm interested in that kind of pattern, rather than that I'm interested in just one of the events. So to do this, to combine these data, we can look at windows, and windows are basically just buckets of time. So so rather than seeing our stream as an endless endless thing that never ends, we think about it as chunks of data, basically. And three interesting types of windows that I want to highlight are these three: just tumbling windows, sliding windows, and session windows. Tumbling windows are just windows that follow up on each other. Let's say you want to analyze an hour of data every time, then it just means that, okay, you analyze the data from 1 o'clock to 2 o'clock, from 2 o'clock to 3 o'clock, etc., etc. A sliding window is actually the same, but then you say, okay, I'm also interested in the window of 1 hour, but I want to apply a slide to that of maybe 10 minutes, so that I'm analyzing my window of 1 hour every 10 minutes. So I not only have a window of 1 o'clock to 2 o'clock, but also I have a window from 10 minutes past 1 till 10 minutes past 2, etc., etc. And interesting thing is then that your event will be residing in multiple windows, because, for example, this timestamp 1 here falls into these 4 windows that are all overlapping each other. And a third type of window, which is interesting, which is actually which Flink is capable of handling, but not, for example, Spark, are session windows, and they are windows that start and stop with a field, triggered by a field in the event itself. And as it's already being said, usually what a session window usually is, for example, the session from when a customer logs on until he logs off. So I might be interested in finding out what the typical behavior of a user is on a website from the moment that he logs in until he logs off. Well, you can do that with defining these session windows and just saying, okay, my window starts when I arrive this kind of data, this kind of event, and stops when I see this kind of event happening. Now, there's some considerations you have to take into account, because windowing seems very nice. It feels like, okay, hey, we finally have some structure in our events. We finally can do something rather than just consume all the events all at once. That's true. Windows is a really interesting concept that is very useful in many ways. But you also have to be a bit careful, because if you define too many windows, or your windows become too large, then things can go wrong, because what Flink essentially does is keeping all of the data of a window in memory. So it stores the data in memory until it can, basically evaluate the window function. For example, make a sum of all the events, make an average, or do a machine learning algorithm on top of that, and then the window is gone again. But if you have a window of, let's say, 1 day, and you evaluate it every minute with a slide of 1 minute, then all this data keeps on adding up, and you can actually run out of memory. Okay, we're going to go one step deeper on the windowing and event timing side, and I think this is an interesting topic that I still want to share, and that is watermarks. Because consider once again the window that we had as an example of, let's say, 1 hour. Also consider that we're looking at the event time. What is then the moment that we start analyzing and wrapping up the window? You would say, okay, when I get an event with an event time which is later than the final boundary of my window. That's correct. So if I have defined a window of 1 o'clock to 2 o'clock, and I get an event time in with a timestamp of 1 second past 2 o'clock, then I would say, okay, this event does not belong to that window anymore. It belongs to the next window. So I'm now going to start evaluating my window of 1 o'clock to 2 o'clock and wrap it up. But there is latency. There is some latency, and an event can also come at a later stage. So while I'm actually already wrapping up my window of 1 o'clock to 2 o'clock, there could still be an event coming in that should have belonged to that window. That has a event timestamp of 1 minute before 2 o'clock. In that case, yeah, it's actually a bit sad, because that event will be gone and will not be analyzed anymore. So what we can do is actually we can build in a little bit of slack, a little bit of waiting time that says, okay, even though we know that we should be evaluating the window, we're still waiting for a little bit of time before we start analyzing the window. Before start wrapping it up, because we allow some late events to arrive. And that small bit of slack, that amount of waiting time is triggered by a watermark. So we can set in our example again, we can set a watermark of, let's say, 2 seconds. That means we allow 2 seconds after the window has passed for events to come in, and after those 2 seconds, we actually start evaluating the entire window. So how does this look in code? Well, in Flink, you have to basically create something called a watermark extractor, and which is a class that has 2 core methods that you need to override. The extract timestamp, which just signals the field that you have for timestamp. Let's say my event is in something called a timed event, and that timed event has a property called event time. Then I would probably say, okay, my event time is just is actually defined by the number of milliseconds in that timestamp. And the other one is to set the watermark, and the watermark in this case is also is defined in the number of milliseconds. And we can, well, this is just a very simple example, because the watermark in this case is actually being defined by comparing it to the system time. So comparing to system time, of course, is a bit dangerous, because the clocks might not be synchronized, etc. But for this example, we just say, okay, I'm waiting 1 second, 1,000 milliseconds, so 1 second in processing time, and then allowing the event to come in. And after my watermark has passed, and I'm starting to process all the events of the window. Okay, we're going to switch to machine learning, because after all, this is what we want to do at the end. We want to, once we have detected a pattern, we've analyzed the data, we have basically aggregated the data, we have detected this pattern, we want to do something useful with it, and usually that is calling a machine learning model. Well, there's a few ways that we can actually do machine learning scoring of a model. And what you probably usually read in courses or in textbooks is that you basically serve your model in an API. So you wrap your model in a bit of an interface that accepts JSON and returns a result, like a score, for example, from an API. That's the way to do it. But then if we are doing this in streaming data, and we are really processing thousands of events per second, and even our windows lead to maybe hundreds of events per second, that's usually not fast enough. because if we do 1,000 API calls to one API, which is not not distributed and maybe not high performing enough, then this can lead to all kinds of lag and all kinds of memory issues again. So another way to do this when you're doing streaming is to persist your models first on disk and then to load them in memory in your stream. And then, so basically what you do is you take an intermediate format of your machine learning model and you broadcast that model across all your nodes in your cluster, so that the model that you want to evaluate is actually readily available to be scored in every task manager of your cluster. And a framework that's really nicely suited for that is PMML, which is an intermediate an intermediate format that can be read by Java programs with the open scoring library. Just added an example here because it's not so well known, PMML, but actually all of the modern data science frameworks and tools have an option to export their models to PMML. The common way to export models is or to serialize them is something like a pickle or joblib, but that's usually when you're working in a Python environment and your API, your wrapper around your API is also written in Python. That's a really nice interaction there to have. But if you're working with big data tools like this that are usually JVM based, like Flink and Spark, PML is actually also a great option. And PML is just XML. There's also JSON representation, by the way. So if you prefer that, then it's also possible. That's called PFA. And this is, but you can see that's actually also quite a human-readable format. We have a regression model here that's exported by sklearn. Well, something like this comes out of it. And the model, of course, has to be scored. So what I said, the first step is to host that model on disk, and after that, we will lazily load it into memory to our stream. So once that's done, we want to call a library called OpenScoring.io, and I added some example code here of how you can do that in Java or Scala code. So again, while you're streaming data, you could use this model, some method like this called score. That accepts an event. In this case, it's not a raw event anymore, but it's a rich business event, or it's already enriched data that contains a full feature set for your model to score, and a PML model itself. And basically, what you do is you prepare some input fields. You call the model evaluate from the PML model, which is handled by the open scoring framework. And then you set the target fields and you fill in the target fields as scores of the model. So we're coming to the end of this session. Want to wrap it up a little bit. A summary of what I just talked about is that, I highlighted a few cases of streaming analytics, or fast data, as we call it. I think it's becoming a very popular subject in a lot of businesses that I've been working for. Typically because now the number of data sources that can produce this kind of data, and also the technology that we can do to handle this is getting much more mature. You have to think about a common pattern when you're analyzing this data. You can't just start analyzing and querying, all the events that you have. First, you have to detect a pattern, so you do something like complex event pattern recognition, complex event processing. After that, you do some windowing and data aggregation, and you apply this in a machine learning model. And of course, that results in another notification or follow-up action. I gave you a bit of an architecture for this, and I pointed you to some tools for these jobs, Kafka and Flink mostly, and then we did a bit of a deep dive into typical streaming problems like event event time, windowing, watermarking, etc. So I hope you've seen a bit of that and scratched the tip of the iceberg a little bit for that. If you want to know more, I highlighted some resources here that are great papers to read. And also there's a course currently on the University of Delft here in the Netherlands, which is fully online that you can take maybe. The code that I have is also on GitLab. It's available in a library called Styx, which is a streaming library written in Scala that has some Flink and some Spark in it. Yeah, and of course, again, you can connect with me on any of the social media platforms. Yeah, we have some time left, so I'm happy to take any questions while I'm here. And but first of all, I want to thank you for listening and enjoy the rest of the conference. Thank you very much.